Good evening, students. Welcome back to the class. So we are going to revise the third chapter of chemistry. Okay, let us understand some of the topics here. It's all about radioactivity. Okay, under this radioactivity, we are going to understand about alpha, beta, as well as gamma rays. Okay, under this radioactivity, the rays emitted by a radioactive substance, and they are alpha, beta, gamma rays, and also about nuclear fission reaction as well as nuclear fusion reaction. Okay, let us understand about fission as well as fusion reactions here, and also we are going to understand about their differences in the reactions. The first question here is, radioactive dating is a technique which can be used to measure the age of rocks, composition of rocks, color of rocks, weight of rocks. Okay, let us look at the answer now. The right answer is option A. Okay, the age of the rocks. To determine the age of the rocks, the term we use it here is radioactive dating. Okay, we are going to date this radioactive elements. Okay, finding out the dates, that is the age of the radioactive substance here. So radioactive dating is a technique which can be used to measure the age of rocks and several such minerals, etc. Okay, we are going to find out the date, the age of these rocks and the minerals, different minerals available in Earth crust. So in this process, the age of radioactive substance is measured on the basis of quantity that is remaining after of the age of the rock. So for example, if a substance it has 12 months, okay, for example, if we consider carbon, okay, carbon is one of an element. So 12 months will be its off life, okay. If the carbon, if it has 12 months of off-life period, that means by the end of 12 months, only the half of the carbon particles would have decayed. Okay, it will undergo decomposition. So the rate of the amount of the material remaining after 12 months, that indicates the age of the material here. Okay, age of the metal that we have chosen carbon here. So this is how we can find out the date, the age of the different rocks as well as minerals, just by comparing it with that of the original one. Okay, it can be done. Okay, radioactive dating, it can also be done by comparison between the absorbed radioactive isotope as well as the decaying products. Usually, as in when we leave it naturally there, it will start decomposing, right? So when it is decomposing, we can compare the same with that of the absorbed radioactive isotope. So based on the color, we can make a comparison, right? So that gives finally, okay, that will finally give us the age of that rock or the mineral that we have. Okay, moving to the next question now. Rutherford alpha particle scattering experiment was responsible for the discovery of electron, proton, nucleus, helium. Okay, let us know the answer now. Here, the right answer is nucleus. So we have discussed about this in the previous class. So nucleus, the discovery of the same nucleus is all done by the Rutherford alpha particle scattering experiment. So he had used gold foil here in this experiment. He allowed all the rays, right? The rays to pass through it, and most of it got deflected here because of the presence of nucleus at the center, right? Because when this rays started striking this nucleus at the center of the atom here, it got deflected back. So this is how it got deflected back. But here the rays which are emerging at this point, since there is a lot of free space here, so it was completely passed through the atom. Got it? So this deflected rays indicated the presence of nucleus, and this final experiment led Rutherford to find out The presence of nucleus at the center of an atom, and where all the atomic mass is present. The mass of an atom resides here in the nucleus. Okay, that is what is the statement given by Rutherford. Now the next question. The credit of construction of first nuclear reactor goes to Niels Bohr, Fermi, Einstein, Oppenheimer. Okay, let us look at the answer now. The right answer is option B. Okay, Fermi is the one. He constructed his own nuclear reactor for the first time using the simple tools. He had constructed his own nuclear reactor for the first time in our India. Clear? So on December 2nd, 1942, Fermi reported having produced the first self-sustaining chain reaction, nuclear chain reaction. Okay, here the nuclear reactor that he had designed, it can carry out the nuclear chain reaction. Okay, and the nuclear reactor control nuclear chain reaction. The nuclear reactor that he had designed here, where the nuclear reaction was taking place, it has a capacity of controlling this complete reaction. It has to be in control. Basically, here in nuclear reactors, okay, nuclear chain reaction has to be in control, okay, and which finally led to the generation of electricity. Got it? So nuclear reactor, let us know about the nuclear reactor. Here the nuclear reactor can also be considered as the heart, okay, heart of nuclear chain reaction, because this is the one which will control the nuclear chain reactions. The nuclear fusion or the fission reactions, it is all controlled by nuclear reactor. Just behaves as a heart, how our heart controls all the parts of, how our heart will pump the blood to all our parts of our body just to supply the energy, right? Here, even this experiment, the nuclear reactors are the one which will also play same role. Okay, so when there is a nuclear chain reaction which is actually taking place here in the nuclear reactors, the nuclear reactors which are present here will control complete nuclear chain reaction that leads to the production of high amount of heat energy. Okay, by fission reaction, it will produce lot of heat energy, and this heat energy, the heat released during this nuclear chain reaction, okay, because of fission reactions. Nuclear fission is nothing but, let us know about the difference between fusion and fission first. Nuclear fission is nothing but a splitting of heavier molecule. Okay, in the fission process, what actually happens, if there is a heavier molecule, it will start splitting down into small equal sized molecules, okay, equal mass molecules. It will again combine with the other nuclei, okay, nuclei of the different atoms to form, it will to split it again further. Okay, so splitting in each of these levels, it will start releasing high amount of energy, and this process of splitting of heavier molecules into simple one, that is called as nuclear fission. Okay, fission, Fission. But here in fusion reaction, the opposite happens. So smaller, lighter particles will combine and it will collide together. If one of the particle comes here and one more can come here, so both of this will collide with each other. When they collide with each other, definitely they are going to release high amount of heat energy. Clear? So this is called as fusion reaction. But when we are talking about nuclear fission or the fission reaction, the energy released here is all controlled by nuclear reactors. Okay, the heat energy which is released during this process, that is then converted into steam. Here the steam is also required for the rotation of turbine, which is used in nuclear power plants, right? Nuclear power, thermal power plants, if you know about this nuclear power plant, right? So there it is. The steam is used to rotate the turbine. Once the turbine rotates, generally, there will be generation of electricity, right? So this is how electricity is generated finally, because of the release of heat energy during nuclear fission as well as fusion reaction. Okay, so moving to the next part. So consider the following statements about nuclear fusion reactors. They work on the principle of fission of heavy nuclei. They usually have tokamak design. They operate at very high temperature. Of these, only 1 and 3 are correct. Only 1 and 2 are correct. Only 2 and 3 are correct. Option D, all of 3, that is 1, 2 and 3 are correct. Okay, let us look at the answer now. The right answer is option C. Okay, only 2 and 3 statements are correct here. They usually have tokamak design and they operate at very high temperature. Okay, so when you're looking at the first statement here, okay, let's consider this first statement now. They work on the principle of fission of heavy nuclei, as I was telling you in the previous slide, right? So nuclear fusion is the one where the lighter particles will come together, okay, nearer to each other so that they will collide with each other. So during this collision, it is going to release high amount of heat energy, okay, with high temperature there. So by this, we can say that the lighter particles are involved, okay, the smaller as well as the lighter particles are involved here in nuclear fusion reaction. It has to fuse together, okay. So this is a one, and here we have second particle. These two particles has to fuse with each other. They have to collide with each other. Only then the energy is released, right? But look at this first statement. So nuclear fusion reactors, so it does not work on the principle of fission of heavy nuclei. Fission means heavy particle will start splitting into two of its nuclei of the same size. Okay, same fragments basically. The nuclei will split into same sized fragments. So that is what we call it as fission. But the statement we have here, the question is all about the nuclear fusion reaction. So this cannot be true now, right? We have to consider this, where the two lighter particles will combine together to release energy. Clear? So when we are looking at the second statement, they usually have tokamak design. So this is a tokamak design that you can see here. Okay. So nuclear fusion reactor work on the principle of fusion of small nuclei. Smaller nuclei will fuse together to form this nuclear fusion reactors. Okay, it works on that principle, and they usually have tokamak design. So your tokamak design that you can see here, it is one of an experimental machine. Okay, tokamak machine that you can see here in this picture, it is one of an experimental machine where that is the one which will carry out nuclear fusion reactions. Okay, so this tokamak design, tokamak machine is the one which can carry out nuclear fusion reaction. So by the end of that, okay, once it carries out this procedure, it will finally release the heat energy. Okay, the same heat energy is then utilized for different purpose. Okay, so this is all about this tokamak design. And so usually this nuclear fusion reaction can take place only at very high temperature. It requires very high temperature, say for about 100 million Kelvin temperature. Okay, it can be up to 100 million Kelvin temperature. So such a high temperature is required for this nuclear fusion reaction to take place. Clear? Because the same can also be seen there in hydrogen bombs, okay, where usually the nuclear fusion reaction takes place. Hydrogen bomb, sun, okay, natural star, as well as the remaining other stars that we can see in the sky there, right, during the night time. So in the stars that is visible, the natural nuclear fusion reaction will take place because the same temperature can be found there. Okay, the core Okay, the core of the star has usually up to this temperature, 100 million Kelvin of temperature, where there will be usually nuclear fusion reaction can be absorbed. Okay, so smaller fusion, smaller lighter particles will collide together to release high amount of heat energy. And all of this will be carried out only if there is a presence of very high temperature. Clear? So hydrogen bomb, it is also based on the same principle, that is nuclear fusion with high temperature. Is that clear? Moving to the next question now. The difference between a nuclear reactor and atomic bomb is that no chain reaction takes place in nuclear reactor, while in atomic bomb, there is a chain reaction. The chain reaction in nuclear reactor is controlled. The chain reaction in nuclear reactor is not controlled. No chain reaction takes place in atomic bomb, while it takes place in nuclear reactor. Okay, let us look at the answer now. Here the right answer is option B. Okay, the chain reaction in nuclear reactor is controlled. Okay, both of this works on the same principle. Okay, both of this will work on the same principle of chain reaction, nuclear fission reaction, but still here in the nuclear reactor, it is completely controlled. Okay, but in atomic bomb, so it is completely uncontrolled. That is why it will usually explode there. Okay. So nuclear fission is a perfect example of the chain reaction, nuclear chain reactions, which will take place, right? So nuclear fission, as I said you, the lighter particles will collide with each other, okay, to form a bigger molecule. And during this collision, it also releases high amount of heat energy. Clear? So in the case of nuclear fission, heavy atomic nucleus, such as uranium, uranium is one of the heavy atomic nucleus. It has a heavy atomic nucleus. Okay. This atomic nucleus of such elements, that is uranium, for example, that disintegrates. Okay. That is, they undergo disintegration. They will split up here to form nearly about 2 equal fragments of the nucleus. Okay. So here it is going to disintegrate to form almost similar sized nucleus here. And during this release, okay, during this disintegration, it also releases large amount of energy, and this energy is used. Okay, so this energy is usually released in the form of neutrons. Okay, the neutrons are released. So when one of the nucleus out of this two, when one of the nucleus splits and strikes the other nuclei of the neighboring atom, okay, if it strikes the other nuclei, the same again continues. It will go and hit the second one, next one, and it will go and hit the next one. So that it will start continuously splitting and splitting out. Okay, when there is a continuous splitting here, so during every splitting, that is during every disintegration, it will start releasing high amount of heat energy. So finally, when we are looking at the net amount of heat energy released during all the complete nuclear fission reaction, that is in this chain reaction. So since it is a chain reaction, if one of this nuclei, it strikes and split this particle, okay, it will go further and it will move further towards the next one. It will start striking here and it will split it here. Okay, it splits and strikes the next one, splits and strikes the next one. That is what actually will happen in chain reaction. Okay, it is a form of linear chain. Clear? And during this chain reaction, so every time once it starts splitting down there, it will start releasing high amount of heat energy. Clear? And the process continues till there is a chain, nuclear chain, till it continues. So now when we are looking at this atomic bomb as well as the nuclear reactor in the question, okay, both of this works on a principle of nuclear fission. Okay, that is the heavier molecule will start splitting down into simple substances, simple particles, simple nuclei. Clear? So, but when we are considering the nuclear reactor here, okay, this one, the nuclear reactor, it is completely controlled by control rods. Nuclear reactor is one of a machine where there will be a presence of control rods. And these control rods are made out of metals, some of the metals such as cadmium or boron. So these are the metals can be used to make these control rods. So these control rods are present only here in nuclear reactor. So this is a one which will control the chain reaction. Okay, it will control. So as and when this chain reaction continues till here. So here we have nuclear reactor. It has a control rods. So this can control and it can stop the nuclear reaction here, or it can slow down the nuclear reaction here. Okay, it is completely in control. But what happens here in atomic bomb? Okay, atomic bomb, here it is not, there will be no any presence of neutron absorber. Okay, neutron absorber are not present here in case of atomic bomb. So the nuclear chain reaction, it keeps on continuing for longer period of time. Okay, there will be no any control during the chain reaction. It is not controlled by anyone here. So finally it explodes and it is very violent, right? We can hear the sound. So it is completely inaudible. We cannot hear. We may damage our ears too, right? So that is what actually will happen. Okay, moving to the next question now. A radioactive substance has a half-life of 4 months. 3/4 of the substance would decay in 3 months, 4 months, 8 months, 12 months. Okay, let us look at the answer now. Here the right answer is option C, 8 months. Okay, so when we are looking at this off-life period of some of the isotopes, but what do we mean by off-life here in chemistry? So off-life is nothing but the amount of time that is taken by radioactive isotope. Okay, so that usually takes 1/2 of the radioactive isotope to decay. Okay, for example, if we have one complete radioactive isotope, okay, so to start decaying, okay, how longer time it takes usually to decay half of its content. Okay, the components of this radioactive material to decay half of its content, how longer time that it is going to take. Okay, that is what we call it as off life. So to decay this part, the time taken by this radioactive isotope, that can be considered as off life. Okay, so this can be compared with that one, the observed radioactive isotopes that we usually familiar with. So by observing with different materials, we can just look at the size, color, or if there is any disintegration, formation, okay, any changes that we can observe physically, that can be identified just by comparing with the fresh new radioactive isotope. Clear? But how to find out the 3/4 of the substance would decay in how longer time it requires to decay here? Look at the question again. The radioactive substance has half-life of 4 months. So if we have a radioactive substance here and it requires 4 months to decay off of it, right? So to decay this part, it requires around 4 months. So now the question is 3/4 of the substance would decay in, okay, this quantity will then decay in how more longer time, okay, how more months it is required to decay this part. So only finally by the end we should get only 1/4 of the radioactive isotope. Only this part of the isotope should remain, right? So to complete disintegration, okay, to start decaying this complete part, how longer time it is going to take, that is what we have to calculate. So given that 4 months is of a time, right? So we can strike out this option. It will never be 3 months, not lesser than this 4 months. And again, it is not even 4. It has to be actually above 5 months, right? So we cannot consider this option now. So when we are looking at this, so 4 plus 4. So half of the particle can decay in 4 months, and the remaining of to decay, again it requires 4 more months, right? 4 plus 4 will be 12. So the question is all about 3/4 of it, not complete part, right? If the question is like to come to start decaying one complete radioisotope, that requires, it can be 12 months. Now the question is all about only 3/4 of this radioactive isotope. So we cannot even consider this 12 months, right? It will never be 4 months. And again, the right option, the remaining option is 8. So this is what we can consider. Okay, 8 months is required here for this radioactive substance to complete its 3/4 of the decay. Okay, 3/4 of its decay. It requires about 8 months. To decay completely, it requires 12 months. And to decay off of it, it requires 4 months. And to decay only this part, okay, 1/4 of it, it requires 2 months, right? So this is how we can calculate. Moving to the next question now. A radioactive substance emits alpha particle, beta particle, gamma particle, all of these three. Okay, let us look at the answer now. So as I was telling you in the beginning itself, right? So radioactive substance, it can emit all these three rays, alpha rays, beta rays, as well as gamma rays, right? So the right option here is option D, all of this. Okay, it can emit both, all three here, alpha particle, beta particle, as well as gamma particle. So all of this, okay, when we are looking at this alpha particle, they are usually positively charged. Okay, positively charged particles, and they usually rotate in clockwise direction. Clear? Beta particles are negatively charged, and they usually, since because of the presence of negative charge here, it will start rotating in anti-clockwise direction. Clear? But when we are looking at gamma particle, what is the charge present here? Okay, it is completely neutral, no charge carrying species. Okay, so it does not carry any of the charge. It is neither positive nor negative. So it is neutral in nature. Okay, since it is neutral in nature, there will be no any charge, uncharged, right? So because of there is no any charge present in this gamma particles, it will always remain undeflected. Even if we are passing electric rays or the magnetic rays, here the radioactive substance which usually emits gamma particles will never get deflected because it does not carry any of the charge. It is always stable. Okay, need not to move anywhere there. So it always remains the same. Okay, so here based on the magnetic field that we are going to provide here to this radioactive isotopes, they have their own abilities to penetrate and pass through a matter. So into a matter, even those particles, okay, alpha particle or the beta particle, gamma particle, if radioactive substances accidentally, if we swallow this, okay, it can start penetrating through our cells, through our tissues of our body, through the organs. Okay, so it can penetrate easily through a matter here. Is that clear? And they always be with different velocity. They always move with different velocities. This is all about radioactive substances. Moving to the next question now. Yellow cake, an item moves smuggling across border. Okay, across border here, and is a crude from the heroin, a crude from cocaine, and uranium oxide, unreformed gold. Okay, let us look at the answer now. Here, the right answer is option C, uranium oxide. Okay, uranium oxide is the one that can be used as yellow cake, and it is used here in smuggling, usually across the border of our India. Not only in our India, so all over the countries, in different countries, all over the world. So there we can see as a smuggling material, illegally they are using this uranium oxide, which is highly poisonous to humanity. Okay, in the form of yellow cake. So these yellow cakes generally denotes various compounds of uranium. Okay, different compounds of uranium. So like just like uranium oxides, clear? Enriched uranium can be used in making illegal nuclear explosive. So this, if there is enriched more amount of this uranium oxides, if it is present there, so that can be highly explosive. Okay, nuclear fission reaction will take place here. So that the particles will break down where there will be no control, because it is completely uncontrolled nuclear fission reaction, right? It follows the same principle. So when there is a fission reaction, it breaks up to explode directly. Okay, so that can be very dangerous to humanity. You have to remember, students, fusion is nothing but usually building up of particles. Okay, fusion reaction where these two will build up together to generate energy, and this energy can be used for positive purpose. So basically to generate electricity, right, to carry out the different reactions. So for positive purpose, that is what we can just understand here. But here when I'm talking about fusion reaction is the one that will be sometimes dangerous, because the atomic bomb that works on the principle of nuclear fission, because it will break down since there will be no presence of nuclear reactors. Sorry, these control rods here, it will go uncontrolled. It cannot be controlled. The nuclear chain reaction, it will go continuous and finally explode violently. Is that clear? Usually in the bombs or in so the sun energy, okay, solar energy. So this is what we will observe there. Okay, and it is dangerous to humanity, not only humanity, so all the animals, plant life, everywhere else. Moving to the next question. So the inexhaustible source of energy of the stars is due to conversion of hydrogen into helium, conversion of helium to hydrogen, decay of radioactive element, excess of oxygen that helps burning and release of energy. Okay, let us look at the answer now. Here, the right answer is option A, conversion of hydrogen to helium. Okay, the energy present in the star, for example, sun, we can take it as an example, right? So here the energy of the sun, that is the solar energy, it's all because of the conversion of hydrogen present there into helium. It is highly efficient one which can release high amount of heat energy. Okay, the energy released from the collapse of gas. So there will be a gas when this gas collapse together. Okay, when it collapse together, high amount of heat energy is released. That is the reason at the center of this star, it is extremely hot. Okay, the core of the stars are very hot, extremely high temperature, where nuclear fusion reaction can take place, right? So when the core is hot enough, the nuclear fusion commences, right? So nuclear fission reaction it requires very high temperature, extremely to about 100 million Kelvin of temperature is required to carry out this reaction. And the same temperature is present here in the core of the star. Okay, it's all because of the collapse of the gases. So it will collapse together. The gas particles which are present here in the stars will collapse together. During collision, it will release high amount of energy. This high amount of energy can be utilized by the nucleus present there to carry out this nuclear fusion reaction. So during this fusion is one of the process where two hydrogen atoms, okay, for example, here we have two hydrogen atoms will combine together to form helium, okay, helium atom. Okay, helium is comparatively bigger than that of the hydrogen, but still the mass of one of this helium is lesser than the hydrogen. When we combine together, the mass that it gives will be lesser, it will be more than this helium. So helium has a lesser mass when we are combining with this, when we are comparing it with two atoms of hydrogen. Okay, the remaining mass here, the remaining mass which is present here can be utilized by these helium particles to release it as energy. Got it? And this fusion reaction that can be seen absorbed here in the stars, it is very efficient process, releasing huge amount of energy. Finally, it releases high amount of energy, and that is the reason the hotness of the sun here. Okay, we can also feel the hotness here, right? During summer days specifically. Moving to the next question now. Which statement is not associated with a nuclear fission reaction? Neutron-induced nuclear chain, nuclear reaction, energy generation in stars, source of energy nuclear reactor that produces electricity, enormous energy is released in an atom bomb. Okay, let us look at the answer now. So the right answer is option B. Energy generation in stars. As I was telling you, nuclear fission, it is not associated with the generation of energy in stars, because here there will be presence of nuclear fusion reaction. Okay, nuclear fusion reaction is the one that can be absorbed in case of stars, because here the hydrogen atom has to combine together to release high amount of heat energy. Clear? So when we are looking at nuclear fission, so neutron induced nuclear reaction, okay, neutron induced, where there will be release of neutron when these will break down, when the molecule, heavy molecule, if it starts splitting out during the splitting, so it will also release us neutron. Okay, so here we can say that it is all neutron induced nuclear reaction. And the second point, that is source of energy nuclear reactor that produces energy, right? It is a source of energy. So in the nuclear reactor, that can be utilized here to convert it as a steam, and the steam is then utilized to turn the turbines that generate electricity. So enormous energy is also released in atom bomb, right? That is all associated with nuclear fission reaction, where heavier molecule will start splitting out into smaller molecules that can release enormous amount of energy here. Got it? Next question. Match column 1 with column 2, choosing the correct sequence. Photoelectric effect, atom, nuclear fusion, spontaneous emission of radiations, nuclear fission, hydrogen bomb. So the options here are option A is A, that we have to match it with P, and B with R, C with Q, and D is with S. Option B tells us that A, we have to match it with Q, B with P, and C with R, D with S. So option C, A with S, B with R, C with Q, and D with P. Option D tells us that we have to match A with R, B with P, C with S, and D with Q. Okay, let us look at the right option out of all of this here. The answer is option D. Okay, A with R, B with P, C with S, and D with Q. Let us match this here. So we have it here. Radioactivity is with, we had to match it with spontaneous emission of radiations, photoelectric effect, emission of electrons from metals, nuclear fusion, hydrogen bomb, nuclear fission, atom. Okay, so let us understand this here. Radioactivity. Okay, radioactivity, it is spontaneous emission of radiation. Okay, there will be in radioactivity material, there will be continuous spontaneous emission of radiation, that is alpha particle, gamma particle, beta particle. All of these are spontaneously emitted out in a radioactive substance, right? So why do we call it as a spontaneous emission then? Spontaneous emission, it's all because of it is a spontaneous, there will be emission of the radiation very spontaneously. It's all because the atoms which are present in a radioactive material, if it excites, that is, if it gets excited, what it will do? It will start releasing the energy in terms of photon. Okay, in the form of photon, it will start releasing energy, and after some time, it will get into the lower energy level. Okay, this radioactive atoms present here will enter to the lower level of energy by emitting photon, and during this process it also releases energy in the form in a random direction. So however, randomly in all the possible direction, it keeps on releasing the radiation. That is the reason we call it as spontaneous emission of radiation. Clear? Photoelectric effect. So photo, the name itself indicates that in the presence of light, right? Light is required when the light falls on the metals. Emission of electrons from metals, that is, when the light falls on the metals, these metals, when there is a fall of light on these metals, usually the isotopes, different isotopes of hydrogen present here in the metal, isotopes of hydrogen will combine together to form helium, right? Hydrogen to helium. Got it? And during this process, it will also release a lot of energy. Clear? So photoelectric effect, it is always related with emission of electrons from different metals. So only in the presence of light, okay, it can convert the hydrogen present there, isotopes of hydrogen, into helium atoms. So when we are looking at this nuclear fusion, so in hydrogen bomb, nuclear fusion reaction is the one that takes place, because hydrogen, the same example here we have, the same part. Okay, we can relate it to even with this. So hydrogen, so smaller molecules, smaller atom of this hydrogen will combine together to form a heavier molecule of helium, right? So these are the hydrogen, and here finally it is going to form a heavy nuclei of helium. That is a fusion reaction. Both of these two are combining together. They are colliding with each other, right? And again, during this collision, there will be a release of energy. Okay, so that is what will actually happen here in hydrogen bomb. Basically, we can observe both fusion as well as fusion reaction. So initially, there will be a fusion reaction while converting hydrogen to helium. And then later, once it explodes, that is because of fission reaction, it will then further break it down. Helium will further break down to release enormous amount of energy. Clear? And nuclear fission reaction that can be observed here in atomic bomb. Okay, it is not atom, atomic bomb. So here we can observe nuclear fission reaction, where the heavy molecule will start splitting out. Okay, if we have a heavy nuclei here, it will start splitting out into smaller fragments of the nuclei, which will usually carry the same equal mass of the atoms. Okay, so during this process, again, it will start releasing high amount of energy. Okay, that process we call it as fission. Fusion is joining together to form a bigger molecule. Fission is it will then split out, okay, to form simple molecules, simple and smaller, lighter molecules. Got it? That is a major difference between these two. Moving to the next question now. Hydrogen bomb is based on the principle of controlled fusion reaction, uncontrolled fusion reaction, controlled fission reaction, uncontrolled fission reaction. Okay, let us look at the answer now. The right answer is option B, uncontrolled fusion reaction. So uncontrolled, the name itself will suggest us that the nuclear chain reaction, it always remains uncontrolled. We cannot control it. Okay, since there will be no presence of nuclear reactors or the controlling rods are completely absent here. So neutron absorber or not presence. Since there will be no presence of the neutron absorber, there will be uncontrolled release of this continuous chain, right? It will keep on releasing high amount of heat energy and finally it will explode, right? That is what we can observe here in hydrogen bomb. And for the first time, it was discovered by one of our American scientists in the year 1952. And it is all based upon the reaction of nuclear fusion. Okay, so small hydrogen molecules will combine together to form heavier helium nuclei. That is what I was explaining till now, right? So in the previous slide. So hydrogen atoms will combine together to form a huge helium molecule. During this procedure, the chain continues. Okay, it keeps on continuing for a longer period of time since it is uncontrolled fusion reaction. And finally, it will explode. Understand? Okay, moving to the next question. So it is highly destructive nature, both this atomic bomb or the hydrogen bomb that we have, all of these are highly destructive nature. They can destroy in a high range. So solar energy is produced by the following reaction: fission reaction, fusion reaction, chemical reaction, none of these. Okay, students, let us look at the answer now. Right answer is fusion reaction. Just now we have discussed solar energy. That is one of the star, right? Our natural star, nearest star, sun. So when we are the radiations emitted by solar energy, right? It's all because of the fusion reaction that takes place at the core of the stars usually. Okay, because of high temperature, very high temperature, which is present at the core. Okay, and in this reaction, to carry out this fusion reaction, it requires high temperature, 100 million Kelvin of temperature, right? Approximately of about that. So this, in the presence of this high temperature, nuclear fusion reaction can take place. So to form helium nuclei, the same, okay? Hydrogen atoms combine together to form nuclear fusion reaction to form, to convert it into helium nuclei. So during this process, it also releases highly energetic neutron. Okay, helium so formed here can release during this conversion. It can release highly energetic neutron and is accompanied with the help by the release of large amount of energy. That is what we call it as solar energy. Finally reaches our Earth, right? So there will be release of lot of high energy. This enters our Earth surface. Okay. So your neutron is one with which will be always occupied, accompanied with the release of high amount of energy. That is what we can observe here in all the nuclear fusion reaction as well as fission reaction, fusion as well as fission, right? Neutrons are released, so that will be usually accompanied with release of energy. Okay. Moving to the next question. So if by mistake some radioactive substance get into human body, then from the point of view of radiation damage, the most harmful will be one that emits alpha rays, neutrons, beta rays, and gamma rays. Okay, let us look at the answer now. The right answer is option D, gamma rays. So when we are comparing with all of the radiations here, all of this can, that is alpha, beta, and gamma rays can, it is capable of damaging our body parts, the tissues or the cells that we have in our body. But still, comparatively, gamma rays are, since they have very high penetrating power, it can reach all the tissues or the cells that we have in our body, even by mistake if it enters our body. Okay, so if this radioactive substance, so accidentally if it enters our body, so these gamma rays which are present in this radioactive substance, since it has high frequency range, it can move faster, very faster, and it also has high penetrating power. Since it has high penetrating power, it is capable of traveling many feet in air and many inches in human tissues. So tissues, we know that a group of cells, right? So here in all the tissues, it can penetrate easily. So when it is penetrating in the tissues, it can damage the tissues that we have in our body, right? So these readily penetrate most materials and sometimes called penetrating radiation. So this gamma rays can also be considered as penetrating because it has high penetrating power. Clear? Moving to the next question now. Which of the following is likely to reach our body via the food chain in the event of an atomic bomb explosion? U-235, that is uranium-235, strontium-90, potassium-40, hydrogen-3. Okay, let us look at the answer now. Here, the right answer is uranium-235. So, by accidentally, if it enters our food chain during atomic bomb explosion, the uranium-235 isotope, all of these are different isotopes of these elements respectively, right? So, this isotope can enter our food chain, and if it enters our body, it can damage the body parts, right? So atomic bomb, we know that it is a nuclear bomb that involves nuclear fission reaction. So huge molecule will start splitting out, right? So during the split, they will start releasing high amount of energy, and the most common isotopes for the fissile reaction. So what do you mean by fissile here? Fissile are the substances which has the ability to control, to sustain this nuclear chain reactions. Okay, they are capable of sustaining nuclear chain reaction, and during this, they also split the neutrons. Neutrons which are present there during the release, it can split these neutrons to release the energy. Okay, such a particles we call it as fissile particles. And for example, here we have few of it. So uranium-235 is one among them. And again, plutonium. Okay, plutonium, that is P235. All these are isotopes again. So all these are considered as fissile reaction. Along with that, uranium-233 is one more fissile product. Okay, fissile particle which can sustain the nuclear chain reaction. So in this event, that is during atomic bomb explosion, what actually happens? The most likely that would enter, most likely isotope that would enter the food chain is uranium-235 among the given options here. When we are looking at all the options here, comparatively, uranium-235 is the one that can enter our food chain along with the soil, clear, or along with the water. Moving to the next question now. Carbon and graphite rods are used in atomic reactors as moderants for sustained nuclear chain reaction through nuclear fission process. In this process, the neutrons are made fast. The neutrons are made fast, the protons are made fast, the neutrons are made slow, and the protons are made slow. Okay, let us look at the answer now. The right answer is option C. Okay, the neutrons are made slow here. So what is the function of this moderants? Why do we have to add these moderants there in nuclear reactors? Because these moderators, okay, moderators like carbon or the graphite, cadmium, right? So all these are the one which is capable of slowing down the neutrons. Okay, it will slow down the neutrons in nuclear reactors. So when these elements are capable of slowing down the neutrons, so we can control this nuclear chain reaction, right? So it is to maintain the chain reaction here. It acts as a moderation here. The neutrons from fission have high speeds, right? So in a chain reaction, we know that it either keeps on splitting out or it will combine together, collide with each other to form a huge molecule. So it is a continuous reaction. And if there is a presence of moderators here, such as carbon and graphite, it is capable of slowing down this nuclear chain reaction. If it is not controlled, what actually will happen? It goes uncontrolled and it releases high amount of energy. Finally, it explodes. Okay, that is what will actually happen. So to avoid this, to prevent this, as a moderation, here the moderators are added. So which can maintain this chain reaction. It will either slow down or it will stop sometimes, well, as based on the situation that we require for. Okay. Okay, students, and by we are completing this part, and thank you for attending class.